Welcome to this scientific exploration of sugar work in candy making. Today we're going to dive deep into the physics, chemistry, thermodynamics, and materials science that transforms simple sugar solutions into hard candies and lollipops. Let's start with a fundamental question. What actually happens at the molecular level when we dissolve sugar in water? Sucrose, which is table sugar, is a disaccharide molecule. When we add it to water, the polar water molecules surround and separate the sugar molecules through a process called solvation. The hydrogen bonding between water and the hydroxyl groups on sugar molecules allows dissolution. In candy making, we start with a sugar solution. But concentration is everything. Concentration is defined as the mass of sugar divided by the total mass of solution times 100%. We typically start with a concentration of 60 to 70% sugar by mass. This is already a highly supersaturated solution compared to what would naturally dissolve at room temperature. As we heat the solution and water evaporates, the concentration increases dramatically. This is the key to candy making. Now let's talk about a crucial thermodynamic phenomenon called boiling point elevation. This is a colligative property, meaning it depends on the number of dissolved particles, not their identity. The equation for boiling point elevation is delta T sub B equals K sub B times M, where delta T sub B is the change in boiling point, K sub B is the ebullioscopic constant for water, and M is the molality of the solution. Pure water boils at 100 degrees Celsius at 1 atmosphere of pressure. But when we add sugar, the boiling point increases. The more concentrated the solution, the higher the boiling point. As we heat our sugar solution, water molecules gain enough energy to escape as vapor, but the presence of sugar molecules at the surface interferes with this process, requiring higher temperatures to achieve boiling. But why does sugar increase the boiling point? This is a question of entropy and vapor pressure. Sugar molecules in solution create order. When water molecules vaporize, they must overcome not just the hydrogen bonds with other water molecules, but also their interactions with sugar molecules. This reduces the entropy gain of vaporization. This means the vapor pressure of the solution is lower than pure water at the same temperature. We need higher temperatures to reach atmospheric pressure and achieve boiling. As water evaporates and concentration increases, we reach specific temperature ranges that correspond to different candy textures. Let me show you the progression. Here's the temperature scale. Thread stage at 110 to 112 Celsius with 80% sugar. Softball at 112 to 116 with 85%. Moving up through firm ball, hard ball, soft crack, and finally hard crack at 149 to 154 Celsius with 99% sugar concentration. You might wonder, why does the difference of just a few degrees Celsius completely change the candy's properties? This is where thermodynamics and materials science converge. The answer lies in water content. Each degree of temperature increase corresponds to a specific amount of water evaporation. Even 1 or 2% difference in water content drastically affects molecular mobility. Viscosity is inversely proportional to water content. As water decreases, viscosity increases exponentially, not linearly. At 5% water content, around softball stage, sugar molecules can still flow and reorganize. The candy is pliable. But at 1% water, in hard crack stage, molecular motion is severely restricted. The material becomes rigid and brittle. Now let's discuss one of the most important concepts in candy making, the glass transition. This is a material science phenomenon that explains why hard candies are hard. First, what is glass? Glass is not a crystal. It's an amorphous solid. The molecules are frozen in a disordered, liquid-like arrangement without forming a regular crystal lattice. On the left, we see crystalline structure with regular, repeating patterns. On the right, we see amorphous glass structure, where molecules are randomly arranged, frozen in place without crystallizing. The glass transition temperature, T sub G, is the temperature below which a material transitions from a rubbery or viscous state to a hard, brittle, glassy state. For pure anhydrous sucrose, the glass transition temperature is around 62 degrees Celsius. However, water acts as a plasticizer. Even small amounts of water lower T sub G dramatically. This is why humidity affects candy stability. As a rough approximation, T sub G equals approximately 62 degrees Celsius minus 10 degrees Celsius times the percent water content. At 2% water, T sub G drops to about 40 degrees Celsius. This is why hard candy can soften on a warm day. The glass transition can be understood through free volume theory, a concept from polymer physics that applies beautifully to sugar systems. Free volume refers to the empty space between molecules. Above T sub G, there's enough free volume for molecules to move and flow. Below T sub G, molecules are packed tightly with minimal free volume. They're essentially trapped in place, giving the material its glassy, rigid character. Above T sub G, molecules have mobility and can rearrange. Below T sub G, molecules are frozen in a glassy state with restricted motion. Now let's talk about crystallization, which is both the goal and the enemy in candy making, depending on what you're trying to make. Crystallization is the process where dissolved sugar molecules organize into a regular, repeating lattice structure. For hard candies, we want to prevent this. For fudge or fondant, we want to control it. Our concentrated sugar solution is highly supersaturated. Thermodynamically, the system wants to form crystals to lower its free energy. The driving force for crystallization is related to the change in Gibbs free energy. Delta G equals negative RT times the natural log of C divided by C subsat, where C is the actual concentration and C subsat is the saturation concentration. Crystallization requires nucleation. This is the formation of a small cluster of molecules in the correct crystal structure, which then serves as a template for further growth. Homogeneous nucleation occurs spontaneously in the bulk solution, but it requires very high supersaturation and is relatively rare in candy making. Heterogeneous nucleation occurs on surfaces, dust particles, or seed crystals. This is much more common, and why we must be careful about cleanliness and stirring. A small nucleus forms, and if it's large enough to be stable, sugar molecules add to it layer by layer, growing the crystal. This is what we want to avoid in hard candy making. So how do we prevent crystallization and keep our sugar in the amorphous glassy state? There are several strategies based on chemistry and kinetics. Strategy 1. Add interfering agents. We add substances that disrupt the ability of sucrose molecules to pack into crystals. Corn syrup, which contains glucose and glucose polymers, physically gets in the way of sucrose molecules trying to organize into crystals. The different molecular shapes prevent regular packing. We can also use invert sugar, which is sucrose that has been broken down into glucose and fructose through acid hydrolysis. These different sugars interfere with crystal formation. The reaction is sucrose plus water yields glucose plus fructose. Adding a small amount of acid, like cream of tartar or lemon juice, catalyzes this reaction during cooking. Strategy 2. Cool the syrup rapidly after reaching the target temperature. This kinetically traps the molecules in the amorphous state before they have time to organize into crystals. Strategy 3. Avoid stirring or agitation once the syrup reaches the final temperature. Agitation promotes nucleation by creating local concentration gradients and introducing air bubbles that serve as nucleation sites. Let's focus specifically on the hard crack stage, which is used for hard candies and lollipops. Why is this stage special? At the hard crack stage, we're at 149 to 154 degrees Celsius. The water content has been reduced to less than 2%. This is critical. We have 98 to 99% sugar by mass. This is an extremely concentrated system. At this stage, the viscosity exceeds 10 to the 6th Pascal seconds. For comparison, honey is about 10 Pascal seconds. This syrup is hundreds of thousands of times more viscous. Most importantly, when this syrup cools, its glass transition temperature is well above room temperature, ensuring the candy remains hard and brittle. Let's analyze what happens thermodynamically as our hard cracked syrup cools from 150 degrees to room temperature. The heat released is Q equals mc delta T, where m is mass, C is specific heat capacity, and delta T is the temperature change. Unlike water freezing into ice, there is no first-order phase transition with a latent heat. Instead, the syrup gradually becomes more viscous. As temperature decreases, viscosity increases exponentially. At the glass transition temperature, there's a dramatic change in the temperature dependence of viscosity. Below T sub G, the material is a glass. The temperature dependence of viscosity near the glass transition is described by the Williams-Landau-Ferry equation, or WLF equation. Log of eta over eta sub g equals negative c 1 times t minus t sub g divided by c2 plus t minus t sub g. This equation shows how dramatically viscosity changes near t sub g. This equation explains why candy texture is so sensitive to final temperature. Near T sub G, a few degrees makes an enormous difference in viscosity. Let's briefly examine the molecular structure of sucrose itself, because its chemistry determines all these properties. Sucrose is composed of one glucose unit and one fructose unit connected by a glycosidic bond. The molecule has 8 hydroxyl groups. These create extensive hydrogen bonding networks, both with water and with other sugar molecules. The hydroxyl groups are shown here. They're responsible for sucrose's high solubility in water and its ability to form hydrogen bonds in the solid or glassy state. Here's a practical question. Why do hard candies eventually get sticky or soft if left exposed to air? The answer is that sugar is hygroscopic, meaning it absorbs moisture from the air. Those hydroxyl groups readily form hydrogen bonds with water molecules. As the candy absorbs even small amounts of water, that water acts as a plasticizer, lowering the glass transition temperature. If T sub G drops below room temperature, the candy transitions from the glassy state to a rubbery state, becoming sticky and soft. This is exactly why hard candies must be individually wrapped in moisture-proof packaging immediately after cooling. If we heat sugar to very high temperatures, above 160 degrees Celsius, we begin to see caramelization. This is a different phenomenon from what we've discussed. Caramelization is the thermal decomposition of sugar molecules. The sucrose breaks down into smaller molecules, creating new flavors and brown color. Sucrose undergoes complex thermal degradation reactions, producing hundreds of different compounds, including furans, aldehydes, and ketones. While some caramelization adds flavor, too much produces bitter compounds and can ruin the candy. This is why precise temperature control is essential. Let's directly compare the softball stage with the hard crack stage to understand the dramatic difference a few percent of water makes. In softball stage, we have 15% water and the glass transition temperature is below 0 Celsius. The material is pliable and prone to crystallization. In hard crack, only 1% water remains. T sub G is around 50 degrees, and we have a hard, brittle, amorphous glass that resists crystallization. From a material science perspective, we can describe the mechanical behavior using stress-strain relationships. Stress equals Young's modulus times strain for elastic deformation. This is Hooke's law. Hard crack candy has a very high elastic modulus, meaning it resists deformation. It's stiff. However, it's also brittle, with low fracture toughness. Once a crack initiates, it propagates rapidly, causing the candy to shatter rather than deform plastically. This brittleness is a direct consequence of the rigid amorphous structure. Without crystalline planes that can slip, the material can't dissipate stress through plastic deformation. Let me emphasize again why temperature control is absolutely critical in candy making from a scientific perspective. Each degree of temperature corresponds to a specific equilibrium water content through the boiling point elevation relationship. That water content directly determines molecular mobility and the glass transition temperature of the final product. The glass transition temperature, in turn, determines whether the candy will be hard, chewy, or sticky at room temperature. So we have this chain. Temperature determines water content, which determines T sub G, which determines final texture. Each link in this chain is governed by fundamental thermodynamics. Modern candy manufacturing uses sophisticated equipment to achieve precise control over these variables. Vacuum cooking allows boiling at lower temperatures by reducing pressure. This prevents excessive caramelization while still removing water. Industrial systems use continuous cooking with automated temperature control to within plus or minus 1 degree Celsius. Cooling occurs in humidity-controlled tunnels to prevent moisture absorption before packaging. Modern factories even use inline refractometers to measure sugar concentration in real time, ensuring perfect consistency. Let me address some common questions about the science of candy making. Question: why does altitude affect candy making? At high altitude, atmospheric pressure is lower, so water boils at a lower temperature. Answer: this means at a given temperature, Less water has evaporated, so you have a higher water content than the recipe expects. You must cook to a higher temperature at altitude to achieve the same final water content. Question: can you make hard candy without corn syrup? Answer: yes, but you need to add an acid like cream of tartar to catalyze the formation of invert sugar during cooking. This provides the interfering sugars needed to prevent crystallization. Question: why do recipes often say to wash down the sides of the pan with a wet brush? Answer: sugar crystals that form on the pan walls above the syrup can fall back in and seed massive crystallization. Washing them down prevents this heterogeneous nucleation. Let me summarize the key scientific principles we've covered today. Boiling point elevation, a colligative property, allows us to concentrate sugar solutions beyond what's possible at atmospheric pressure. Temperature and water content are precisely correlated through thermodynamic equilibrium, explaining why small temperature differences matter so much. The glass transition phenomenon creates the hard, brittle structure of candy when T sub G is above room temperature. Preventing crystallization requires both chemical interfering agents and proper technique to avoid nucleation. Water acts as a plasticizer, dramatically lowering T sub G and changing mechanical properties even in small quantities. The entire process beautifully illustrates the interplay of solution chemistry, thermodynamics, kinetics, and material science. Making hard candy is fundamentally an exercise in controlling phase behavior and kinetics. We're creating a metastable amorphous solid, a glass, by rapidly cooling a supersaturated solution while preventing crystallization. Understanding the underlying science allows candy makers to troubleshoot problems, adapt to different conditions, and innovate new textures and products. These same principles of glass transition, plasticization, and crystallization control apply to many other material systems, from polymers to pharmaceuticals to metallurgy. This demonstrates how fundamental science can transform an empirical craft into reproducible engineering while still preserving the artistry involved.